exercise 6H, question 18b, perhaps a bit confusing because it's in a more generalized form. When you get to question 18, you're finding distance between two planes. Now the formula, we derived it as distance from an external point to a plane, but you can use this formula to find the distance between two planes. You just need to have a point on the other planes, all right? So maybe you've got a plane there and you've got some other plane here, right? If you knew a point on plane 1, you could find the distance to plane 2. Is the shortest distance, which I guess would be sort of like that. All right. Now, in our question, these planes are parallel. They haven't given me actual equations or specific equations. They've just said ax plus by plus cz plus d1. And they've got the same equation but with a d2. So this is a situation where you will have planes looking like this, right? Parallel planes. Because the constant's different, they're not coincident. They're not the same plane. As soon as you just change that constant, they become parallel planes, so that the x, y, z coefficients, if they're the same, you're dealing with this situation here, parallel planes. Now, this is kind of interesting because you can choose a point anywhere on one of the planes, and then you need to get to the second plane. You'll need the equation of the second plane, right? The ax plus by plus cz minus d equals 0. And on here, you'll need some point, some x1, y1, z1, right? You just got to keep it in your short-term memory. Keep it in mind. Which plane are you getting the point from, and which plane are you using the equation to get your normal vector, so to get your ABC and to get your magnitude, etc. Right? Okay. So, probably using up too much space. I think I will get the point from plane 1, somewhat arbitrarily. Could use either. And then I'll use plane 2 for my normal vector. In this case, it doesn't matter because they have the same normal vector. In fact, let's just write that down. The normal vector will be the A. These are little a's. Lowercase a, it's a bit dodgy, B and C. Okay, so I want a point from plane 1. Now, okay, I could write just x, y, z, but that's not going to be overly useful. If to get a point, so I think I need a numerical, but say I had 2x plus y plus, I don't know, 3z, and it equaled 12. 12 has got lots of factors. One way I could find a point easily is just to make, let the x and the y equal 0. Let. All right, so this would be where it's crossing the z-axis, this plane. But that's fine. So any numbers that satisfy this equation must be a point on the plane. So if we said 2 times 0, and then we could work out what the z would have to be. Y is just 0. plus 3 times some z has to equal 12. And then we could, from that, that's 0, that's 0. We could work out that z could be 4 if we did that. And then we could say, well, this point is really easy to get because I made 2 of the variables just equal 0. This point is 0, 0, 4. So that's one way you could do it. And that's what we're going to use here because we don't actually have any numbers to work with, so we can't start guessing. We want something as specific. I mean, like for this one, I could have said, just to continue on, I could have said x is 2, y is 2, and z is 2, I think. That would have given me 4 plus 2, yeah. All right, so here's another point on the plane, 2, 2, 2. Because it will satisfy this equation, I'll get 12 if I do that. Or I could have said x is 1, that gives me 2, y could be 1, and z could be 3. Because I'll have 2 plus 1 plus 3. All right, so that must be a point on the plane. Anything that works must be a point. So let's use the idea of finding the z-axis intercept. Right, so on plane 2, no, I was going to use plane 1. On plane 1, a point on plane 1 could be 0, 0, z, which means we would have a times 0 plus b times 0 plus c times z has to equal minus d1, and therefore the z value would equal minus d1, can I just fit it in here, on c, and all of this means that the point on P1, that's plane 1, is 0, 0, minus D1 on C. Okay, just draw a line here. Now we're ready to go to our distance formula. So we'll get distance equals excuse me, a times 0. Just write 0. All right, so I'm starting over here. I'm doing the a times the x1, but the x1 is a 0, so that will be 0, plus b. For us, that's a lowercase b. Lowercase b times the y coordinate there, 0, so that's another 0. Nice. Now the z times a c, okay, so that will be c, that's coming from the normal vector, times the z coordinate, which I worked out, so that's times by minus d1 on c, and we'll need our d, which comes from plane 2, d2. So I'm using plane 2 as the plane, I'm using plane 1 as the point, right? I can't say, I can't use plane 1 to plane 1 because there's going to be no distance, right? So I've got my point from plane 1, should have written plane 2. I'm using plane 2 to satisfy the A, B, C, D, right? So that there is actually some distance between them, right? And then that will be all divided by the magnitude of the normal from plane 2, which is the same as the normal from plane 1 in this instance, because I've already explained that these planes are parallel. So, well, their normals are also parallel. Now, if you look at what's left up the top, you're going to get the modulus. So in this numerator here, you're going to get the modulus of minus d1 plus d2, which is probably nicer to write as d2 minus d1. Let's do that. d2 minus d1 divided by a squared, b squared, c squared. Okay, so that's it. It's done. If this value d2 minus d1 came out as a negative, we would have to make it positive. That's all the modulus says there. All right, I'll stop that there. I think I might actually do one more question for you guys, so stay tuned.